How are you, my friends? This is lecture 18 of the pre-calculus course, graphing cotangent and cosecant functions. Please, you can review lecture number 17 before that on the graphs of tangent and secant. And now we will go to cotan and cosecant. Now, I mentioned before, the cotan function has a period pi as the tan, and the cosecant, they have a period of 2 pi as the secant and sine and cosine also. The vertical asymptote we have mentioned earlier, it's a vertical line that the graph approaches but does not intersect. Now the cotangent, we can start by plotting some points. I start from 0, pi over 4, pi over 2, 3 pi over 4, until pi, from 0 to pi. So I see cotan of 0 will be cosine of 0 divided by sine of 0. That is 0 in the denominator, so it will give me undefined. Also, cotan of pi will be cosine of pi divided by sine of pi, which will be undefined. So I can see in the first period of the cotangent, at 0 we have a vertical asymptote, and at pi also we have another vertical asymptotes. Plot the points in the middle, you will see these points. So this is the graph of the tan. You can take any x there, replace it in the cotangent function, then you find the value of y. So there are two vertical asymptotes here in the first period. Now you can see the complete graph. See, in the previous slide, we have seen only from 0 to pi. You see this graph here? Green maybe, from 0 to pi. And here, then pi to 2 pi, 2 pi to 3 pi. So every pi we have one period. Now the x-intercept. It's very important to know how to find the x-intercept of this cotan. So the x-intercept, put y0. If you put here y0, then the cosine will be 0. When the cosine of x will be 0, when x will be pi over 2 plus n pi, where n is integer. Also, you have to know how to find the vertical asymptotes of the cotangent. Cotangent function, we look at the denominator to find the vertical asymptotes, where the denominator is equal to 0, which means sine x is equal to 0, so x will be n pi. Cotangent function has no amplitude because there is no maximum and there is no minimum. Cotangent function is odd. You can see that in the table. So cotan of minus x is equal minus cotan of x. We'll see that also in the coming lectures. Now, to find the domain of cotangent function, we know cotangent function is equal cosine of x divided by sine of x. So we need all the vertical asymptotes. That means where the value in the denominator is 0, that means where x sine of x is equal to 0, which is x equals n pi, where n is integer. So the domain of the cotan is all real numbers except n pi, where n is integer. Remember now, the argument only x. If we change the argument, then all this argument should be equals to n pi. Now the domain of general cotangent, we have d plus a cotan argument. See here, argument can be anything. General argument, we have seen before what is the general argument. So the domain now, we take the argument equals n pi because we look at the denominator to find the domain because we need the vertical asymptotes. So from the argument equals n pi where n is integer, solve for x, you will find the equation of the vertical asymptotes. So domain will be all real numbers except the vertical asymptotes where n is integer. To find the domain of cosecant, see the cosecant, 1 over sine of x, the same method as finding the domain of cotan of x, which is cosine of x divided by sine of x. See, the denominator here is the same. X-intercept, easy to find x-intercept. Let y is equal to 0. So you let y equal to 0. That means the cosine of x is equal to 0. Put the argument equals pi over 2 plus n pi, where n is integer. Then find all the values of the x. Let's find the domain of this function. 6 minus 5 cotan of 4 bracket x minus pi over 12. Let's find the domain. So to find the domain, we have to look for the correct argument. Multiply by 4 here inside, 4x minus pi over 3. That's the correct argument. Now, we need the domain. That means we have to find the vertical asymptotes, the equation of the vertical asymptotes. That means where the denominator is equal to 0. So put the argument equals n pi, where n is integer. So 4x minus pi over 3 is equal to n pi. Take pi over 3 on the other side, divide by 4. So x will be pi over 12 plus n pi over 4. This is the equation of the vertical asymptotes. See, every time we put n is an integer, 1, 2, 3, 0, minus 1, minus 2, minus 3, you will get a vertical asymptote. So now the domain will be all real numbers except all of these. Pi over 12 plus n pi over 4, where n is integer. Now the general cotan, A cotan k x minus b. I mentioned before, this is the argument. Both are the same here. So the period for the cotan as the tangent function, pi over k, the range all real numbers, the phase shift. If b is positive, it goes to the right. If b is negative, it goes to the left. To graph cotangent function, remember, it's different from tangent. Take the argument equals to 0 to find s, and then take argument equals to pi to find e, where the first period ends. Now, just to remind you, in the tangent, we take the argument minus pi over 2, and here we take the argument pi over 2. In the cotangent, we take from 0 to pi, just to remind you. To find the domain, I mentioned before, put the argument is equal n pi, where n is integer, then the domain will be all real numbers except vertical asymptotes. To find the x-intercept of any cotangent function, put the argument equals pi over 2 plus n pi, where n is integer, find x. Now, this is a very important example. A, B, C, 3 parts. We have to graph 2 periods of this cotangent function, 2 cotan 3x plus pi over 4. Now, after that, we need to find the number of vertical asymptotes in this interval minus 7 pi over 12 until 7 pi over 12 closed. After that, we need to find the sum of the vertical asymptotes. So B and C are related because to find the sum of the vertical asymptotes, you have to find them and then you add them. So that's a long, nice question here. So let's see. This is the 2 cotan 3x plus pi over 4. You can take 3 if you like. Then it becomes 3 out x plus pi over 12. These are the same function, different forms. This one you can find the correct argument, and this one you can find the shifting. See x plus pi over 12. On the left, you see minus pi over 12. Because the cotan at the beginning from 0 to pi, see it goes now on the left, see? X plus pi over 12 on the left shifting. So let's say the period starts, argument is equal to 0. This is the argument, equals to 0. So this is S here. So you see minus pi over 12. Now the period ends at argument equals pi. See the argument here is equal to pi. So pi minus pi over 4, and then divide by 3, it will be pi over 4. So from minus pi over 12 to pi over 4. How do you know the other period? Just add pi over 4. You see, this is the end of the period, the end here. Add another period. So pi over 4, add one period, plus pi over 3, it will be 7 pi over 12 there. You can add another period, another period, another period. Now, the same function, let's find the vertical asymptotes. Put the argument equals n pi. So 3x plus pi over 4 is equal to n pi. Take pi over 4 on the other side, divide by 3. So x will be minus pi over 12 plus n pi over 3. Now, what do? We take the interval given here, minus 7 pi over 12 to 7 pi over 12. We create an inequality. We make it. We make inequality. We take the equation here of the vertical asymptotes, minus pi over 12 plus n pi over 3, between closed, sometimes they are open, sometimes one closed, one open, minus 7 pi over 12, 7 pi over 12. Now we add pi over 12 on each side, you see, and then we multiply by 3 over pi to find n. You can do it easily, please. And then n will be greater than or equal minus 3 pi over minus 3 over 2 only, less than or equal to 2. Let's find all the integers here. This is minus 1.5. So we go to minus 1, 0, 1, and 2, because this is already closed. If this is open, we don't take 2. Now in part C, let's use the equation of the vertical asymptotes, x equals minus pi over 12 plus n pi over 3, where n is integer. And we have found already 4 n's. N is equal to minus 1, 0, 1, and 2. Every time we replace n there, like if I put here minus 1 just to show you, minus pi over 12 minus pi over 3. Multiply by 4 to find the LCD 12, so you get minus 5 pi over 12. Same for n equals 0 here, and then n equals 1, n equals 2. Then you add the 4 vertical asymptotes. When you add all these numbers, you get pi over 3. Now another nice question here. F of x is equal to cotan 1/3 of 6x minus 3 pi over 2. Over this interval, closed, see here now we have closed, minus pi over 4 to open 7 pi over 4. We need the number of x-intercept and then the sum of all x-intercept. This can be a question. This can be another question. So the x-intercept, we put y is equal to 0. Remember here we have to find, see this is 1 over 3, 6, 3x minus pi over 2. Multiply the 1 over 3 inside the bracket, you will get 2x minus pi over, this is the correct argument, and this is the interval closed and open. So to find the x-intercept of the cotan, we put the argument is equal pi over 2 plus n pi, where n is integer, because the cotan of the x is equal to the cosine of the x divided by sine of the x. So in the x-intercept, we put y equal to 0. That means the cosine will be 0, and the cosine will be 0 at pi over 2 plus n pi. So we take the argument here, 2x minus pi over 2 is equal to pi over 2 plus n pi. Take this on the other side, becomes pi, divide by 2. So x equals pi over 2 plus n pi over 2. This is the equation of the x-intercept, remember. Now we create an inequality. This is closed minus pi over 4 closed, and this is open 7 pi over 4. And in the middle here, we put the equation of the x-intercept. And then we solve this compound inequality. Here we subtract, we put minus pi over 2 in each side, and then we multiply by 2 over pi. We will get n between closed minus 1.5 less than 2.5. So now the n values, the integers, are minus 1, 0, 1, and 2. See, 2 is less than that. 4 x-intercepts. Now here we use the equation of the x-intercept we have found in part A. X equals pi over 2 plus n pi over 2. And then we replace the values of the n's, minus 1, 0, 1, and 2. So if n is equal minus 1, you put here minus 1, x will be 0. If n is 0 here, x will be pi over 2, because we are finding the x-intercept. If n is 1 here, x will be pi. If n is 2, x will be 3 pi over 2. So I add all the values of the x, 0, pi over 2, pi, 3 pi over 2. The LCD here is 2. So this becomes here 2 pi over 2. It will be 6 pi over 2, which is 3 pi as the sum. Now, if you look at the cosecant We know cosecant function 1 over sine of x. That's the reciprocal. So to graph cosecant, it's very important that you graph the sine first. See, the sine starts from 0, it will go to pi, and then it will go to 2 pi. That's one period. All the zeros of the sine, see, these are 3 zeros at 0, at pi, at 2 pi. This becomes the vertical asymptotes of the cosecant, because the cosecant 1 over sine, every number will make it 0 here, which is 0, pi, or 2 pi. It will be the vertical asymptotes of the cosecant. And also cosecant is the reciprocal. So any number there, let's say the sine of x is 1/3. So 1 over 1/3 becomes 3. See? So the graph of the cosecant will be above the 1, that's the reciprocal, and then below the -1. So the range of the cosecant will be from -infinity to -1 closed, union 1 closed to infinity without shifting. And now the domain, all real numbers except n pi. Now the general cosecant is d plus a cosecant kx minus b. The period for the cosecant p is equal to 2 pi over k. Just to remind you, the same formula, p equals 2 pi over k. You can use this for cosecant, secant, sine, and cosine. But you cannot use it for tangent and cotangent. You can check lecture 15, please, if you like, to see the graphs of the sine in details. Because we need to graph the sine, then we graph cosecant. And the range in general for the secant and cosecant, I mentioned before, -infinity to d minus absolute value of a, union d plus absolute value of a until infinity. A is the coefficient of the cosecant, it can be positive or negative. D is the shifting up or down, it can be also positive or negative. The domain of the cosecant, we mentioned before, domain of the cosecant is the same way as the domain of the cotan. Why? Because they have the same denominator. See, to find the domain, you have to look where the denominator is equal to 0. So we put the argument equals n pi, where n is integer, and then we solve for x. That equation, we call it equation of vertical asymptotes. Domain will be all real numbers except the vertical asymptotes. Let's graph one period of this function, 3 cosecant 2x plus pi over 2. So the argument here is so clear. 2x plus pi over 2 is the argument. If you write it in this form, 3 cosecant 2 out plus pi over 4, you see this is the shifting on the left. See, the sign was at 0 there. Now it is at minus pi over 4. So the phase shift here is minus pi over 4, shifting on the left. So let's take the argument is equal to 0 to find the s where the period starts. So put the argument here, 2x plus pi over 2 is equal to 0. X will be minus pi over 4. That's the first vertical asymptote. Take the argument is equal 2 pi. 2x plus pi over 2 is equal to 2 pi. X will be 3 pi over 4. This is where the period ends. And then you can divide the period into 4 equal parts like we did in the sine. So in the sine is lecture 15. So it will be minus pi over 4, 0, pi over 4, pi over 2, 3 pi over 4. Then when you draw the sine, you draw it as dashed. See, dashed. Then above the 3, because the coefficient here of the cosecant, which is a, is 3. And then minus below minus 3. Okay. Now let's see here. We have cosecant 3, cosecant 2, x plus pi over 4. Let's find the domain. And let's find the number and sum of the vertical asymptotes in this interval, open minus pi over 4 to closed 5 pi over 4. Let's see the domain of the cosecant. So let's find the equation of the vertical asymptotes. Now cosecant, remember cosecant 1 over sine. So you take the argument equals n pi. The argument in this case will be 2x plus pi over 2 is equal to n pi. Take this on the other side. So x will be minus pi over 4 plus n pi over 2. Let's call it star. So this is the equation of the vertical asymptotes. See the equation of all the vertical asymptotes. If you need the domain here in part A, all real numbers except all these vertical asymptotes. Minus pi over 4 plus n pi over 2, where n is integer. Now we have to find, see part B, we have to find the number of vertical asymptotes and the vertical asymptotes and the sum. That means we add them. So to find the vertical asymptotes in this interval, see this is the given now, minus pi over 4 to 5 pi over 4 closed. We create an inequality. We put all this star here, open minus pi over 4 to closed 5 pi over 4. So I put the equation here, minus pi over 4 plus n pi over 2, open and closed. And then I solve this compound inequality. So I add pi over 4, pi over 4, pi over 4 to each side. Then I multiply by 2 over pi. So when I add, I get here 0. See, minus pi over 4 plus pi over 4. This is 0. And pi over 2. When you add here, you get 6 pi over 4, which is 3 pi over 2. Let's multiply by 2 over pi to find the n. So n will be open greater than 0, open here, less than or equal to closed 3. So what are the n's? Greater than 0, it will be 1, 2, or 3. So there are 3 vertical asymptotes in this given interval. Let's find them. Take n is equal to 1, put it in the equation star here, you see? Put n 1 here. And then put n is equal to 2, and put n is equal to 3. So let's try 1 here. Minus pi over 4 plus pi over 2, multiplied by up and down by 2. So you get pi over 4. Then put n is equal to 2. So x will be 3 pi over 4. Put n is equal to 3 there. So it will be x 5 pi over 4. You add them, pi over 4, 3 pi over 4, 5 pi over 4. So this is 9 pi over 4 is the sum of the vertical asymptotes in this interval. Now I will leave for you some questions to practice on lectures 17 and 18. All the exams questions to practice. This is a function tangent. Find the interval when the graph is above the x. You have to graph it. This is the equation given here, and that's a tangent. So try to find the equation. Question number 3 is the secant. 5 secant 3 bracket x minus pi over 6. Find the sum of the vertical asymptotes over the interval closed minus pi over 2 to 7 pi over 6 also closed. Graph the cotangent absolute value of the cotan of x given the function. Graph it first, better. Where the graph of this function is increasing over the interval minus pi over 2 to pi over 2. And then given the secant here, it's 3 over 2, secant 2 in the bracket, 2x minus pi over 2 minus 2 over 3 outside. Find the domain and the range. Given this is a nice one. 3 cosecant pi over 5 minus x over 2 outside the bracket minus half. If the period is capital D, you find the period by the formula, and the phase shift, which is a small b, remember in the general, we call it capital T here, phase shift. Find the value of D plus T, capital D plus capital T. This is the equation of a cosecant function. Try to imagine it, see the period, and then find the equation. And the last one is a nice, this is a cotan pi bracket 1 over 4x plus half over the interval minus 4 to 4. So here we have, I think, 4 parts. Graph it. See, we graph it. Let's graph from minus 4 to 4. Then find the zeros of the function from minus 4 to 4. Find the vertical asymptotes from minus 4 to 4. Find them. Like, what are the vertical asymptotes? You don't have to add them. And then where the graph is below the x from minus 4 to 4. So this is like 4 parts in question number 8. That's why I write here, nice. Now here you find all the answers of the 8 questions and their parts. For complete solution, please, you can visit or see or watch the video on graphs of tan, secant, cotan, and cosecant. Lectures 17 and 18, pre-calculus, all the exams questions. Thank you for watching. If you like the video, you can subscribe and share it with your friends. Just to remind you, this is pre-calculus course, lecture number 18. I hope I can see you in another video with another topic. Thank you very much.